Okay, let's talk about energetics of running. In order to do this, remember we need to really use terms energy, work, and power. So it's important to have those down. I have videos on those to make sure this might be a good time to go back and watch the energy, work, and power uh, videos because we're gonna build on that. But I'll give a quick little summary of energy, work, and power here. Energy is the capacity to do work. And remember, energy comes in all different forms: chemical, electrical, mechanical, nuclear, what have you. Energy has the units of joules. Work, from a mechanical perspective, is a force applied over some distance, or distance. Work and energy share the same set of units of joules. Okay, that's important. And we're going to need to know that going forward. The third term that we need to be familiar with is power. Now, from a mechanical perspective, power is simply the rate of work done, or the equation work over time. If we insert FD for work over time, we actually derive another equation for power, and that's force times velocity. It's how fast a force is being applied. And we'll use both these forms of this equation. And it's also important to know that in the literature, especially in the exercise physiology literature, they will often refer to rate of work done, and they'll use that first equation. But mathematically, we often calculate force times velocity, and I'll show you that. It ends up being one less math step if we're using force and velocity. Now, the units for power are watts. And conceptually, what's really important is to understand that power represents how fast energy is transformed from one form to another. So, how fast are we taking chemical energy and converting it to, or transforming it to electrical energy, or how fast mechanical to electrical, or any of those? Any transformation of energy from one form to another happens at a rate, and that rate is represented by the term power conceptually. Okay, why is this important? Well, to understand energetics of running, we need to understand metabolic processes. Now, you know metabolic processes. You've had exercise physiology class, you've had some anatomy and physiology classes, even functional anatomy, anatomical kinesics. You probably have touched on this a little bit. Metabolic processes describe how we take, in essence, chemical energy and transform that chemical energy to mechanical energy. Again, in essence, we're actually transforming chemical energy in food to ATP, adenosine triphosphate. And then that adenosine triphosphate is used in the process to shorten the sarcomere, which ends up creating a force on the tendons, pulling on the bones that across that form a joint. All right, so here's just a very basic chemical schematic. We have food. We add in oxygen, which we get by extracting oxygen from the air that we breathe in. And from that, we use metabolic processes that yield ATP, adenosine triphosphate, carbon dioxide, and water. Now, thinking back to our thermoregulation rules, the key rule is the energy at time one has to be the same at time two. But if we just look at the energy at these two moments in time, we'll actually see that they won't be equal to each other. And if we have about 1 unit of energy here, we'll only get about one third of the energy units over here. So about 30%. Where's the rest of the energy? Well, the rest of the energy goes off in terms of heat, and escapes this process and ultimately balances out that equation where the energy at time one is equal to the energy at time two plus any heat. And again, we're only about 30% efficient in the human body, maybe 33%, but we don't get picky there. uh, in terms of transforming the chemical energy in food. And I always like to think that food is nothing more than stored chemical energy. So it's some potential energy, and that potential energy is ultimately transformed over the energy which will help us move. So in essence, this would be mechanical energy, but this is never one for one. And so we have heat that's lost in the system. This is the same thing in your car. You put gas in your car and you drive, and that conversion of chemical energy and gas is not perfectly efficient to yield the force to drive the wheels. And that's why your engine gets warm as you're driving. That's why you have a radiator to try to keep it cool. Same thing in the body. That's why we sweat. That's why we have cooling mechanisms in the body to try to dissipate any heat that's generated. Same thing in the car. Now, to understand metabolic processes, because that's what we're really trying to get to, we have really two broad categories of approaching metabolic processes, and that's direct and indirect calorimetry. Yeah, I spelled it wrong first. That's all right. Direct calorimetry, what we're actually doing is directly measuring the heat that is generated in this transformation of potential energy over here over to this energy over here. So to measure that heat, what we do is we put the food in a special container, or if we're doing a person, we put the person in a special room that is very sensitive to measuring changes in temperature. And so we directly measure that heat because that's a thermal regulation process. Well, hardly any of us do that type of work because the instruments are a little limiting in terms of exercise. And so instead, we'll use an indirect way to determine this heat. All right, it's indirect because we're measuring VO2 through our metabolic cart, our metabolic instruments, or what we're doing is we're having person breathe in a instrument where we're measuring the air drawn into the lungs and we're measuring the air expired from the lungs. And interestingly enough, we are actually analyzing the expired air. And what we're determining using that instrument is how much of that air expired has oxygen and how much of it is CO2. And if there's less oxygen in the expired air, then we know that oxygen was used by the body, and that oxygen would be used in this process up here. So we're actually measuring expired air, but then we're using that to understand what oxygen was used during the system or during the metabolic process. And we also understand the CO2 expired directly there. So direct calorimetry, we're directly measuring the heat. Indirect, we're measuring VO2, and we're using that to determine the heat. Now, why do I say heat? Because this is a calorimetry device, okay? And what we're actually interested in this metabolic processes is the calories that are generated here, or the heat that's generated. Calorie is a measure of a heat, or calorie is a measure of heat. 1 calorie is the amount of heat needed to raise 1 gram of water, 1 degree Celsius. So how much heat do we need to be able to do that is a calorie. All right, so calorie is nothing more than a measure of heat. So when you look at your labels on food stuff, you'll see calories. That's telling you how, in essence, how much heat can be generated. All right, we're going to need to know that in just a bit. Now, let me switch gears and let's talk about a graded exercise test, which you're familiar with because you've taken a physiology class. This is where intensity of exercise progresses from something light to something really fast. And I am going to do down here, this will be intensity of exercise for this graded exercise test. And what I'm going to do is I'm going to put speed here. So I'm going to start off slow. I'm going to put concepts down, and then this is going to be fast over here. And so maybe the speed is like 4 miles per hour, 5 miles, whatever. And it increases in equal increments, ultimately until you get to max effort somewhere over here. And over here, this is really easy. And somewhere in here, this is moderate. And speed, we'll use units of, and I'm going to use sort of weird units right now because I know what I want to do. I'm going to use meters per minute. This could be miles per hour, it could be meters per second. I'm going to use meters per minute because I know what I'm going to do next. On this axis, on the y-axis, I'm going to put VO2. I'm going to put that dot right there. I've mentioned this before in some other videos, but the dot is important because it represents a rate. And in this case, I'm going to use liters per minute. So remember, this could be mLs per kg per minute, but in this case, I'm going to use liters of oxygen per minute. The kilogram, if I work that in here, is just normalizing these data to body mass. And then it just gives a little bit more of an equal comparison between different body sizes. But I'm going to leave the kilograms out for now, just because it's going to be easier for me to show you some of the math here of what's happening with running energetics. All right, so this is running slow, and this is my VO2. Well, if you increase my speed at equal increments, what happens is VO2 will increase at a linear rate. Something weird can happen out here at this max effort. So I'm going to leave this sort of a question mark at this point, because the max part is not important for this part of discussion. It turns out that only about a third, or maybe 20% of the tests may actually plateau VO2. The others, other 70%, 80% of tests will continue to see an increase in VO2, but it may not be linear at that stage. But at this submax region, this is a very linear relationship between VO2 and speed. And I would venture to guess that you're all very comfortable with that relationship. Okay, so if there's something awkward about this relationship, it's time to stop and think and shoot me a message, because this is really important to understand that this is a linear relationship here between speed and VO2. The harder or the faster the speed gets, the harder the exercise. The harder the exercise, the more VO2 we're going to consume. Okay, so now what I want to do is I want to calculate the slope in here. Now, if you remember, slope is rise over run, or in this case, it's change in liters per minute. So let me do it down here. I'm just going to try to get slope. It's rise over run, or in this case, it's change in y, which is change in liters per minute, over change in x, which is change in meters per minute. Now you can see why I use meters per minute for my speed. And if I do my math here, you remember, when you have a fraction divided by a fraction, you multiply the numerator by the inverse of the denominator. And I get units of liters per m, or liters per meter. And this is liters of oxygen, an amount of oxygen per distance. That's what this is. Okay, so let's just stop and think about this. What this is telling us is the amount of oxygen that someone is consuming to run a given speed. Okay, so it's the total amount of oxygen. It's not the rate of oxygen consumption, it's the total amount of oxygen consumed. All right, so let's look at this. Let's draw this out a little bit more. I'm going to go to another set of notes here. And I'm just going to line up my blank page with this one here. I'm going to draw this plot again. I'm going to put VO2, but without the dot now, and I'm just going to put liters of oxygen, okay? And down here, I'm going to keep speed, and this is going to be meters per minute still. Again, I could put something else, but slow, fast. All right, And what I'm going to do is I'm going to go up and calculate the slope of this line right here. I'm going to put a dot down here to represent how steep that slope is. I'm going to move over here and do the same calculation. Well, if you notice, that slope is the same steepness as this slope. So it's going to be the same number here. Same thing here, same here, and same here. All of these slopes are equivalent. So I get a plot that looks like this. This may look a little foreign to you, but this is speed down here and liters of oxygen consumed over here. What this is telling me is a whole new piece of information. It's actually the same information as the previous plot, but it just looks different. What this is telling me is that the amount of oxygen consumed for a speed is, I'll leave the M in here. The amount of oxygen consumed per distance is the same for every speed here. So the amount of oxygen consumed is the same per distance. Or, I would say for a given distance. Okay, for a given distance. All right, the amount of oxygen consumed, liters, is the same for a given distance. That's what the per M is. That's what I should have had it to begin with. Wow, that's weird. Okay, but it's not that weird. If I run, a speed here and then I'm running faster here, the time that I'm running that distance is going to be less here compared to here. So I'm having less time to actually consume that oxygen. All right? But I need to do it at a faster rate because I'm going to end up with the same amount of oxygen when I'm running fast as when I'm running slow. So think about exhaling air into a big balloon. When you're done running, the amount of oxygen or air that you would have, really oxygen, but I'll say air now, that you expire into that balloon is going to be the same here as here. You just would have done it at a faster rate when you're trying to run faster. But the total amount of oxygen that you've used to cover that distance is exactly the same. What we do is we call this energetic cost of locomotion. And the unit for energetic cost of locomotion is units of oxygen, liters of oxygen over a distance. And sometimes you do mLs per kg per minute, doesn't matter. But now you have distance in your denominator. So that's what this is here. Oops, energetic cost of locomotion. And what this is telling us is for all these speeds, their energetic cost is the same, but I'm doing it faster here. So the rate of energy transformation is greater here than here, but the total amount of energy consumed or used to cover that distance is the same. Why? Because VO2 is an indirect measure of the metabolic processes. It's an indirect measure of amount of heat generated. It's the indirect measure of calories. So let's draw this back to calories. All right. I'm going to take that same plot and do this. Because VO2 is indirect calorimetry, and that is telling us, in essence, how much heat is being generated for running these different speeds. I'm going to put calories over here. This is going to be the same as that. And what this is telling us is the number of calories used to cover a given distance, calories per meter, the number of calories to cover a particular distance is the same regardless of speed, but it has to happen faster when I'm running faster. So whatever this calorie is, maybe this is 100 calories, I need to generate that 100 calories fast if I'm running fast, or if I'm generating 100 calories, I'm just doing it slower, so I'm taking longer. So if I'm running a 5-minute mile, it takes me 5 minutes to run 1 mile. That's 100 calories. If I'm running a 10-minute mile, okay, that's twice as fast. Okay, so that's what I said, 5-minute mile here. So if I'm running a 10-minute mile here, that takes me 10 minutes to run this mile. That's 100 calories. If I run 5 minutes per mile, which is faster, that's 5 minutes. That's half the time, but the same number of calories, the same number. But I needed to transform that energy from one form to another at a faster rate. Energy transformation at faster rate, but same amount of energy transformed. Okay, same amount of energy transformed as running slower over here. So from running 10 minutes per mile, that takes me 10 minutes to cover that mile. If I'm running 5 minutes per mile, which is faster, that's 5 minutes every mile, I'm still consuming the same amount of calories. I'm still generating the same amount of heat. One just happens faster than the other. And you know that. You need to be able to transform that chemical energy at a faster rate than when you're running faster than when you're running slower. But the total amount of energy you used is independent of speed. And for the most part, there's good data out there that support that concept, okay? But this is energetic cost of locomotion, and calories is a unit of heat, and calories and joules are interchangeable. In the mechanical world, we'll use joules more. In exercise physiology and nutrition, we'll use calories. But in essence, they represent the same thing. It's just a conversion from one set of units to another. Okay, so energetic cost of locomotion is this plot right here. Now, if you look up energetic cost of locomotion, you may actually see a plot if you do this on the y-axis, and this would be liters per distance, okay? And down here is speed. So I'll use meters per minute just to stay consistent with what I did before. And this would be what we would see for running, which is what I've derived up here, running. And for walking, what's interesting is we would typically see a different type of response. This would be walking. I'm not going to go into detail here. I do this more in physiology of endurance performance. But what this tells us is the amount of energy used to cover a given distance is very dependent on how fast you're trying to walk. Very dependent. So if we walk too slow, we're actually going to increase the energetic cost of locomotion. If we walk too fast, we're going to also increase our total number of calories needed to cover a particular distance. But there's some speed which you will yield the least amount of calories to cover a particular distance. Interestingly, that's almost always your preferred walking speed. You almost zero in on that speed. What's also interesting is as you walk faster and faster and faster, eventually you're gonna decide to start running. Where you decide to start running is not where these two lines cross, okay? But somewhere near here. But then once you do start running, the total number of calories used to cover a distance is the same. It's independent of speed. And that's because there's a linear relationship between VO2 and speed. So that should tell you there's a nonlinear relationship between VO2 and speed for walking. Okay. All right. So I wanted to get energetic cost of locomotion under our belts, and I'm going to follow that up with some more information on energetics of running. All right. Thank you.